we've all been there, right? That momentary sting of a paper cut, maybe?
Oh, definitely. Or
Yeah.
something a bit more serious that leaves a mark.
Exactly. And you wonder, how does our body actually, you know, fix that, put itself back together?
It's an incredible process.
So today, we're doing a deep dive into exactly that. Wound healing, scar formation. It's quite a journey.
It really is. From that first second after an injury to, well, the long-term changes in our tissues.
Our mission today, to figure out how the body's repair crew works, what makes a good scar versus maybe a bad one.
And the tiny molecules pulling the strings behind the scenes.
Right. You've shared some amazing insights and stories with us, and we're excited to walk you through them. Okay, let's unpack this.
Absolutely. And what's fascinating here is that healing isn't just one thing. It's dynamic. A whole sequence of events.
Not just slapping a patch on it.
Not at all. Understanding how it works is crucial, whether it's a tiny cut or, say, major damage to an organ. The body's ability to repair is amazing, but it's complex. It's always balancing, fixing things perfectly with just making sure the structure holds together quickly.
Okay, so let's start relatable. That small, clean cut.
Right.
Like, imagine a 24-year-old woman chopping veggies, oops, nicks her finger, clean cut, maybe needs a couple of stitches, cleans it, gets it stitched, and maybe 3 weeks later you can barely even see it. Skin's normal, finger works fine.
That's the ideal scenario. That's what we call healing by primary intention.
Primary intention.
Yeah.
Okay, so what's happening underneath?
Well, the key is minimal tissue loss. And critically, the underlying structure, the basement membrane, is mostly intact.
The blueprint is still there.
Exactly.
Yeah.
So the body can aim for true regeneration. Think of it like hitting restore factory settings. Neutrophils rush in first, like tiny vacuum cleaners for debris. Then macrophages arrive. They continue cleaning, but also start signaling for the next stage. The really profound insight for you here, if that basement membrane is intact, the body prioritizes regenerating the original tissue. It avoids significant scarring.
So that clean cut is basically the best case scenario, aiming for regeneration.
Precisely.
But what if the damage is, ongoing or just much bigger? That's when things can go a bit wrong, right?
That's where we see a really stark contrast. That's chronic inflammation. Think about the vignette you shared, a 56-year-old man with chronic Hep C.
Right. The fatigue, the swollen abdomen.
Exactly. And a liver biopsy shows these fibrous septa, basically little walls of scar tissue building up inside his liver, blocking normal function. That's cirrhosis.
So totally different from the finger cut.
Completely different. Here, the injury isn't a one-off thing. It's persistent. So you get this constant, low-grade activation of macrophages and lymphocytes are always fighting.
And this is where those molecules come in. TGF-beta, you mentioned.
Yes, exactly. What's fundamentally different in this chronic situation is the constant switching on of molecules like TGF-rho transforming growth factor beta and also PDGF, platelet-derived growth factor.
Okay.
These aren't just letters. They're powerful signals. TGF-B especially, it's like the foreman for scar building. It tells fibroblasts, those are the cells that make collagen, to go into overdrive.
Build more scar tissue.
Right. And over time, the normal working liver tissue, the parenchyma, gets replaced by this dense, non-functional fibrous stuff.
Yeah.
If we connect this to the bigger picture, continuous damage pushes the body away from regeneration and towards excessive scarring, fibrosis. And that really messes up organ function.
Wow. So the repair crew, facing constant trouble, switches from careful rebuilding to just throwing up scar tissue supports, even if they get in the way?
That's a good way to put it.
Okay, maybe a quick timeline would help anchor this for, say, normal skin healing.
Good idea. So first 0 to 3 days.
Yep.
That's acute inflammation. Neutrophils dominate, a blood clot forms, stop the bleeding, clean up. Then, roughly 3 to 7 days, macrophages take over, stay cleaning, but now they're also signaling. Fibroblasts start moving in, and crucially, angiogenesis kicks off.
Angiogenesis, new blood vessels.
Exactly. You need fuel and building blocks. This new pinkish, bumpy tissue, that's granulation tissue. It's rich in blood vessels and has that early type 3 collagen, softer stuff.
Okay, so that's the first week or so. Then what?
Then the remodeling starts. After about 2 weeks or so, that initial type 3 collagen gets broken down and replaced by the much tougher, stronger type I collagen.
Here's where it gets really interesting.
It is. And here's a detail many people don't know. The enzyme doing that switch, collagenase, it needs zinc to work properly.
Zinc. Huh. So diet matters even for scar quality.
Absolutely. No zinc, poor remodeling.
Right.
Then over months, the scar matures. It becomes less vascular, fewer blood vessels, and dense with that strong type I collagen. It's quite an engineering feat, even if the end result isn't always perfect skin.
Right. So we have the ideal healing and the chronic kind that leads to fibrosis. But sometimes, even with a single injury, the scarring itself is the problem. It gets excessive.
Indeed. We've all seen scars that look different. Think about the vignette of the 30-year-old man with a deep burn on his arm. Months later, it's healed, but there's a raised, maybe reddish scar.
Yeah.
But crucially, it stays exactly within the borders of the original burn.
Okay. Confined.
Exactly. That's a hypertrophic scar. It often happens with secondary intention healing, like with burns or big wounds, where the edges can't just be stitched together. The body has to fill a bigger gap. There's often an excess of type 3 collagen early on, but the key is it respects the boundaries.
Okay, hypertrophic means raised but contained. How is that different from, those really prominent scars that seem to bulge out and spread?
That's the key difference. That's the keloid. Picture the other vignette. 19-year-old woman, ear piercing, but now she has this shiny, firm growth that's spread way beyond the original piercing hole.
Right, it doesn't stay put.
Exactly.
Yeah.
That's the fundamental distinction for you, the listener. Hypertrophic. H for held inside. The wound boundary. Keloid. K for hell keeps growing beyond the boundary.
That's a great mnemonic.
It helps. Keloids involve excessive fibroblast activity, tons of collagen, both type 3 and type I, and unlike hypertrophic scars, they generally don't shrink over time. There's also a known higher incidence in people with darker skin, suggesting a genetic component. This raises an important question. Why do some people form keloids and others don't? We don't fully know.
Fascinating. And these scarring issues, they aren't just skin deep, are they? This happens in organs, too.
Absolutely. And that's often where the functional impact is most severe. Take the 63-year-old man who had a heart attack, a myocardial infarction.
Yeah.
Months later, imaging shows part of his heart wall isn't moving, it's akinetic. Why? Because the heart muscle cells there, the cardiac myocytes, they died, and they don't regenerate.
No coming back from that.
No. So the area gets replaced by scar tissue. Dense, type I collagen. It patches the hole, which is vital,
Yeah.
but that patch doesn't contract. It impairs the heart's pumping ability.
Wow. So the scar saves the structure but ruins the function?
In a way, yes. And we see similar things elsewhere. Chronic pancreatitis, the pancreas gets scarred up. Pulmonary fibrosis, scar tissue in the lungs, makes breathing incredibly hard. Kidney interstitial fibrosis scarring impairs kidney function. All driven by chronic inflammation leading to significant scarring. It really shows the double-edged sword of this repair process.
It's truly incredible, the complexity. But as you said, this isn't random. There are specific signals controlling all this. Let's circle back to that master conductor you mentioned, TGFA. It's the scar promoter.
It absolutely is. TGF is central to fibrosis. It doesn't just tell fibroblasts to make collagen. It tells them to make lots of collagen and fibronectin, the main stuff of scars.
Okay.
But it does more. It also decreases the activity of enzymes that would normally break down the extracellular matrix, so it promotes scar building and inhibits scar removal.
So it locks the scar tissue in place.
Precisely. That's why it's such a key player in hypertrophic scars, in keloids, and definitely in that organ fibrosis we discussed, liver cirrhosis, pulmonary fibrosis. It's driving that tough, fibrous architecture.
Okay, so TGFA is the architect. But surely it's not a solo act. What other signals are in this molecular orchestra?
Oh, definitely not solo. It's a whole ensemble. You've got VEGF, vascular endothelial growth factor, and FGF fibroblast growth factor.
What are the vessel builders?
Exactly, the vascular engineers. Crucial for angiogenesis, getting those new blood vessels into the granulation tissue. Got to have supply lines.
Makes sense.
Then there's PDGF, platelet-derived growth factor. Think of it as a recruiter and proliferator. It sends out signals drawing neutrophils, macrophages, and fibroblasts to the site, and it also nudges them to make more collagen.
Okay, getting the workers and materials there.
Right. And then for the surface, you need EGF, epidermal growth factor. That's all about the epithelial cover. It tells the skin cells on the edge to multiply and migrate to close the wound surface.
Covering it up.
Yep. And then for the long game, strength and quality, you have collagenase. That's the remodeler enzyme, swapping out weaker type 3 for strong type I collagen. And remember,
Zinc dependent.
you got it, zinc dependent. And working alongside, often in balance with TGF-air, are the MMP's matrix metalloproteinases, another family of enzymes involved in degrading and remodeling that extracellular matrix, shaping the final scar.
So it's a complex balance of building up and breaking down?
Precisely. And this balance is sensitive.
Yeah.
Which brings us back to, well, deficiencies. We mentioned zinc. Severe vitamin C deficiency. That messes up collagen synthesis itself. You get weak, unstable scars. Scurvy, historically.
Right.
So it shows how basic nutrition directly impacts this incredibly complex molecular process.
Yeah.
What's fascinating here is just how interconnected everything is.
It really is. The precision is amazing, but also the vulnerability, which makes you think, if these growth factors are so fundamental, so powerful, do they show up elsewhere? Maybe where we don't want them.
That is exactly the right question. And the answer is yes.
Mm-hmm.
The same signals that heal a cut can be, well, co-opted in disease, particularly in tumor development. It's like the body's tools being used for the wrong job.
Okay, this is where it gets really unexpected. How does healing relate to tumors?
Let's look at the liver again. It's a great example. The most common benign liver tumor is called a hepatic hemangioma.
Okay, benign, so not cancer.
Correct. It's actually a vascular malformation, like a tangle of dilated blood vessels. And guess what drives its growth?
Let me guess. VEGF, the vessel builder.
Bingo. Angiogenesis is key, so VEGF is the most important cytokine involved. FGF and PDGF play roles too. These things are usually harmless, often found by accident on scans that look very vascular. And here's a critical point for you. Biopsy is a big no-no. Risk of major bleeding.
Wow, okay, good to know. So VEGF drives that benign growth. What about actual liver cancer?
We're like hepatocellular carcinoma or HCC. This is malignant and often arises from chronic liver damage, Hep B, alcohol, cirrhosis.
The stuff that causes chronic inflammation and scarring?
Exactly. So in HCC, you still have VEGF driving angiogenesis tumors.
Yeah.
Tumors need blood supply. But because it often grows out of that scarred cirrhotic liver, TGFS is also a major player.
The scar promoter.
The very same. It's contributing to the environment that allows the cancer to thrive. HCC often produces a marker called AFP alpha-fetoprotein, which we can measure in the blood.
So the healing factors are kind of twisted. VEGF builds vessels for the tumor, and TGF is involved because of the underlying scar tissue.
You got it. It shows how these fundamental biological processes, angiogenesis, fibrosis signaling, can be exploited in disease. It also highlights why treating liver cancer is so complex, especially when it arises in a cirrhotic liver. You're dealing with both the cancer and the underlying damage. This raises an important question. Can we target these factors therapeutically?
That's a huge question. Okay, so this deep dive, wow, it's taken us from a simple cut finger all the way through the body's amazing, sometimes flawed repair kit.
From acute healing right through to chronic fibrosis.
We've seen the key cells, the crucial growth factors like TGFF and VEGF calling the shots for better or worse.
Shaping how we heal.
And then this unexpected twist, how those same signals can get caught up in diseases like liver tumors. It's a really surprising link. So what does this all mean? What's the big takeaway?
I think the big takeaway is that understanding this delicate dance, the balance of all these cells and signals, isn't just, interesting biology. It's absolutely fundamental to the future of medicine.
How so?
Well, think about it. If we understand these mechanisms deeply, maybe we could develop therapies to minimize bad scarring. Or maybe promote better regeneration in organs that currently just scar up, like the heart or liver.
Or even target diseases like fibrosis or maybe some cancers by blocking these signals.
Exactly. Imagine tuning down TGFF in pulmonary fibrosis or blocking VEGF in certain tumors. It's already happening to some extent, but there's so much more potential.
It really makes you appreciate the body's default processes.
It does. Consider how amazing it is that our bodies can perform these intricate repairs, often without us even noticing. But also how these finely tuned systems can go wrong when the signals get crossed or stuck in the on position.
Yeah.
So here's a final thought to maybe chew on. What does it truly mean for the future now that we can identify and potentially start to tweak these incredibly precise molecular signals that control everything from healing a scratch to driving a disease like cirrhosis? Where does that power lead us?